All right, today we are going to talk about chi-squared tests for homogeneity and independence, which are the last two kinds of chi-squared tests in Unit 8. So today we are going to just recap real quick that goodness of fit test from last time. So remember, on a previous episode of AP Stat, we talked about a goodness of fit test. In a goodness of fit test, you have one population of interest and one categorical variable. So you're going to reach in and take one sample from one population and ask everybody one question. And the idea is that you're looking for a distribution of several hypothesized proportions and see how your sample measures up to that. So what is going to happen is your hypothesis is going to be, we hypothesize that the true distribution of the categorical variable is like P1 is 20%, P2 is 30%, P3 is 50%, and we're trying to see how well does our sample fit this data. All right, so a chi-squared value is something that helps us determine how close our values are, our expected values are to our observed values. So one of the things we know is that our expected values are what you get when you take the sample size times the proportion that you would expect in that category. So that hypothesized proportion generally in a goodness of fit test. So for example, if you believe that 20% of the Skittles should be red, then you need to take the sample size 100 times the 20%, and you get that you would expect 20 Skittles in that particular category. The chi-squared distribution is always right skewed, and what we notice if our chi-squared values are small, that means that our observed values are very similar to our expected values. And if our chi-squared values are larger, then our observed values are different than what we expected, and that seems unusual. So the farther we get away from zero with our test statistic chi-squared, the more unusual our sample results seem compared to what we expected to happen. All right, remember that if you are looking for a p-value for a hypothesis test for chi-squared, that is always going to be a right-tailed test. Your chi-squared value is the boundary marker, and the area to the right of that is going to give you that p-value. You can find that p-value in your calculator by reading it off of the calculator. You can also find that p-value by using the table on the very back of the formula packet, and you can use your calculator to compute it by hand if you know the chi-squared value by using a chi-squared CDF. One of the things that we do know is that as the degrees of freedom increases, your curve is going to become more symmetric and less skewed right. But degrees of freedom in a chi-squared test is that categories minus 1. So it's going to take quite a few categories for you not to see this right skew anymore. Also, the p-value for this test, remember, a p-value is the probability of getting results like ours if the null hypothesis is true. All right, so a homogeneity test and an independence test both come from a two-way table. And when I mean two-way table, that means I need you to imagine that you've got a table with labels on both sides, and you've got multiple rows of values. Now, there's two situations in which you could get data like this. The homogeneity test is when you have these two-way tables that have data running down both sides of the table, and those categories on both sides actually represent more than one group and one variable. So a homogeneity test occurs when you have two populations of interest, okay, two populations of interest, or 3 or 4 or 5, multiple groups. You can do as many groups as you want, but there's going to be at least two. And you have one question that you're asking everybody in this group. So you might go and compare the color distribution of all regular size Skittles packages to the color distribution of the like jumbo family size package. Like, is the distribution going to be the same in both kinds of packaging? Or maybe you want to compare the distribution of number of freshmen, sophomores, juniors, and seniors at Avon High School versus comparing them to Plainfield High School. So it's kind of like comparing one pie chart to another. So what we're looking for is very similar to the two population tests from Unit 6, where we did P1 equals P2. But instead, we're going to be looking for, does the whole distribution for population 1 match the whole distribution for population 2. So we're looking for a whole pie chart equals a whole pie chart. This one could look something like we're looking for there's no difference in the distribution of favorite flavor of Star Sours candy across the population of all adults and all children, versus there is a difference in the distribution of Star Sours candy across the populations of all adults and all children. So if I wanted to compare these two groups, adults and children, and see if they have different flavor preferences, I would use a homogeneity test. Okay, so you see my little picture at the top. We're going to look for two groups and one question. So in your notes, you're going to see example, and it has to do with soccer players and non-soccer players and whether or not how many concussions they've had. Okay, so in this question, I have definitely three groups of people here. Three groups. I have soccer players, non-soccer players, and non-athletes. And I only have one question that I've asked them, how many concussions that you have. So I'm using that variable, number of concussions, as a categorical variable. And I'm curious to see, is the distribution of number of concussions, not just 0 or 1 or 2 specifically, not just a specific proportion, but is the whole pie the same? Now, in Unit 2, we would have looked at a segmented bar chart like the one you saw listed, and we would say, do the distributions look the same, kind of using a visual inspection? But sometimes it's difficult to see the differences that seem fairly pronounced in what we're looking at right here. And so that's where the chi-squared test can help us. It can say, is this different enough? How likely would it be to get results like these if the original populations did look the same? So your homogeneity test, again, is kind of this idea of, I want to look at the distribution of one variable, the whole pie, not just one slice like we did in Unit 6, but the whole pie against multiple groups. And that homogeneity part, that prefix of that word, that helps us talk about sameness. Do these groups look the same? Do these groups look the same? All right, the other part of this, my null and alternate hypothesis, will literally be that. Remember, the null hypothesis is a hypothesis about sameness. So we would say something like the distribution of number of concussions, there's my variable, the distribution of the variable, meaning the whole pie, is the same for each category of individual. And my alternate hypothesis would be that same statement, but an idea of difference. Now, a chi-squared test for independence also deals with a two-way table, but instead of comparing several groups with one question, instead we're going to have one group with two questions. So you see my picture, it's all one group, and there's a blue and a red question mark. So we have two questions. So one population of interest and two variables. So you're going to take one sample and you're going to ask everybody in that group two questions. And what we want to know is there a relationship between these two variables in this group? So instead of comparing two groups, we're looking for a relationship between two variables. I want to know, are these variables independent or dependent? So your hypotheses might say something like, there's no association between owning an iPhone and favorite color in the population of Avon High School students. In other words, these are independent variables. And your alternate hypothesis would be something like, there is an association between iPhone ownership and favorite color in the population of Avon High School students. These are dependent variables. So remember that the null hypothesis is always this statement of equality. So independence goes with the fact that the distributions would look the same, and dependence or association is associated with the idea that these variables, the distribution is different. All right, so again, in your notes, there's this example, and it's talking about a middle school music and sports survey. And so what happens is we take a sample of middle school students and we ask them two questions. My two questions are, do you play an instrument and do you play a sport? And so everybody answered my question. I have two answers from every person. And so I'm not trying to compare instrument players to sports players. I'm looking at middle school students in general. And I'm looking, are these two variables independent or dependent in this population? This is where I would have this chi-squared test for independence. So my two variables are my two questions that I ask. I can see those on the two sides of my two-way table. And I could I could make a picture of this. It does look like these variables might be dependent, because it looks like you might be more likely to play a team sport if you play an instrument in this population of middle school children. All right, so again, this chi-squared test for independence, if we were going to look at the null and alternate hypotheses, the null hypothesis would be that idea of sameness, that independence. So I would say there's no association between playing a team sport and playing an instrument in the population of middle school students. The variables are independent. And with the alternate hypothesis, I would say there is an association between playing a team sport and playing an instrument. The variables are dependent. Okay, so one of the things you have to be able to do is find expected counts, because one of the conditions for inference is that all expected counts has to be greater than 5 for a chi-squared test. But it's a little bit different because it's a two-way table. So before, you were able to just, the proportions were probably stated in the problem, like we had the one about the cars, and one car was 19%, one car was 35%. Or we said like Skittles are the same, so you were able to take 100%, divide it amongst 5 categories and get 20%. But with a two-way table, it's a little bit trickier to determine the expected counts. But it's not impossible. In fact, there's a really quick way to memorize something, and then you can just use that, or you can kind of reason through. Here is the way to reason through this. If we are talking about these expected counts, I have one variable here, number of concussions, and I have 3 groups. And if the distribution of the variable is going to be the same across the 3 groups, then that means I would expect the percentage of soccer players, of non-soccer players, and of non-athletes who got 0 concussions to be the same in all groups, so that when I drew my bars, that wedge is going to be the same all the way across that. So is that the same for each group? So how would we figure out what to do for this chi-squared test of homogeneity? So I would think, well, I would expect this percentage to be the same all the way down. So the percentage of 0. So the first thing I would do is I would figure out of the grand total, how many zeros are there? Okay, so out of the grand total, I'm going to look at that marginal distribution that we talked about in Unit 4, marginal distribution. And I've got that 158 out of 250. 158 out of 250, or sorry, 240. 158 out of 240. So that's the number of total people out of the 240 total people who had 0 concussions. All right. So if this is if these two groups look the same, then if 65% of everybody has had 0 concussions, then I would expect 65% of each of these groups to have 0 concussions. So what I would do is I would compute about 65% of each group. So I would take my soccer players, there were 91 soccer players, times about 65% is 59.9. I would take my non-soccer players, and I would have my 96 times that 65 and get 63.2. That would be my expected count. And my non-athletes, I would get about 65% of their total, 53, and expect about 34.9. So remember, the ones in the table are my observed counts, and then these numbers right here that we've computed, those are my expected counts. Now, this is a great way to think about this, because this is what independence looks like, and this is what independence looks like. This is what two groups looking the same looks like for either homogeneity or independence. The idea that all the percentages in this category should be the same as that grand total. So if I would go back and compute this conditional distribution, I would get 65%, 65%, 65%, 65%, all the way down. Okay. For some people, though, this doesn't cut it. This is not a great way to think about it. So you can also use this little thing that you can memorize. The expected count is always going to be the row total times the column total divided by the total total. Row total times column total divided by grand total. So for example, if I want to find the expected count for this cell, soccer players who have 0 concussions, I would take the row total, 91, and the column total, 158, and then I would divide by the total total. So 91 row total times 158 column total divided by row total, 240. That gives me that same 59.9 that we had before. And you'll see that is my expected count for that cell. So in your notes, you'll see where I've calculated the expected counts for several different rows here. And the one that we really want to know is we really want to know what the smallest expected count is. So if you're looking for the smallest expected count, that's going to be the one that has the smallest column total and the smallest row total. So in this case, the smallest expected count would come from the non-athletes because they have the smallest row, and the 3 or more, which has the smallest column. So that would be that non-athletes and That would be this particular cell right here that currently has 0 people sitting in it. So I would take 53 times 15 divided by 240 to find the expected count for that particular cell. The other thing when you're talking about this matrix, I want you to remember that the numbers are, when you're talking about a set of numbers in a table like this, you can also concern this as a matrix. But we're always going to be interested in the matrix of observed counts. So we're going to always talk about this matrix as if those totals didn't exist. For example, in this picture, this we would say has 3 rows and 4 columns. We're not going to include the totals in the size of this matrix. So I used to teach my finite class that this was a remote controlled matrix. You always list the rows first and then the columns second. And if you get confused about what's a row and what's a column, remember columns hold up buildings. So they have to go this way because if they're this way, your building falls down. Okay. So in this table, we can think of it as this 3 by 4 matrix. All right, so the other thing that's different about a two-way table is degrees of freedom. So remember that degrees of freedom for a categorical variable are categories minus 1. But technically, we have categories going across both sides of our matrix. So what we're going to do is we're going to have categories minus 1 on both sides. And as the product of that is going to give our degrees of freedom. So for a chi-squared test based on a two-way table, which means if we're talking about a chi-squared test for independence, or we're talking about a chi-squared test for homogeneity, then our degrees of freedom is going to be rows minus 1. That's like the categories on the row variable, times columns minus 1, that's the categories on the column variable. So in this case, again, we're not including totals. We're going to have that 3 rows and that 4 columns. Our degrees of freedom would be 3 minus 1 times 4 minus 1, or 2 times 3, which is 6. So this would have 6 degrees of freedom. Okay. So there's an example in your notes that says find the expected value, and we're talking about observed. They asked people, are you a Colts fan and are you male or female? And everybody answered. And if we would like to find these expected values, again, we would want to show our work always for the smallest expected value. So I would look for the smallest row column total. They're both the same, 1,200. And I would look for the smallest row total, 250, and I would divide by the total. So for example, no and male, that would be row total times column total divided by total and get 125. And since both of those column totals are the same, both of those would be 125s. Over here, I've done the math in my calculator for the top row as well, and you can see that that would be 1075 for both of these. Okay. To find the chi-squared value, if you were going to do this by hand, remember you need to take the observed minus the expected and square it and divide by the expected. So in our case, remember the ones in the table are the ones that you have observed, and then we would subtract that expected value that we calculated. In this case, this chi-squared comes up to 11.16. To find degrees of freedom, I'd look at this and say there's actually 2 rows and 2 columns. Remember, those total rows don't count. Observes values only. So 2 minus 1 and 2 minus 1, that gives me degrees of freedom of 1. So this only has 1 degree of freedom. So that's probably about as skewed right as this thing can be. All right. So the other thing about setting up a chi-squared test is going through these phantoms steps. So one of the things that's a little bit different about the two-way test is that you're not going to use any variables in your hypotheses. Your variables are always written in words. So the only reason that we have P parameter in our phantoms is because your null hypothesis has like P equals 0.5. So you have to explain that P is the proportion of stolen cars and not the proportion of all cars, for example. Because these null hypotheses don't have any variables in them, there's nothing you have to define. So parameter, we're going to be phantoming on these instead of phantoming on these because there's literally nothing to define here. So the hypotheses for homogeneity, you're going to have no difference in the categorical variable across these populations. The distribution looks the same for different populations. Whereas the alternate hypothesis is going to be, there's going to be a difference in this variable across these populations. So remember, homogeneities, you have one question that you've asked of multiple groups, and you want to know, is the distribution of the answers to that question the same across these multiple groups? With independence, you're going to have one population and 2 variables. So you're going to have something like, there is no association between these two categorical variables in my population. Or you could say these two categorical variables are independent. Your alternate hypothesis is going to be that the variables are associated or that the variables are dependent. Okay, so when we write these, no variables, so no parameter to identify. All right, now, on your notes, I've got these written in a couple of different ways. You can see on the left, those are what comes straight from the College Board people. So that's what the College Board people say you should have. Over here, highlighted on the right, this is the way you could write a homogeneity test. It's a little bit different, but it kind of gives you the same meaning. Okay, and then again, you've got your next page here, you've got your independence. Okay, on the left, this is what College Board says Ho and Ha should be. And on the right, this is another way of saying that. So you could say variable 1 and variable 2 are independent instead of saying there's no association. Those are saying the same thing. Okay. So as far as the assumptions and conditions, remember we have random 10%, and it's not approximately normal because it's skewed to the right because it's chi-squared. So remember, for independence, your data should be collected from a random sample because you're randomly sampling and then you're asking those people 2 questions. For homogeneity, you either need a stratified random sample or a randomized experiment. So a lot of times homogeneity will be an experiment with multiple treatments, and you're randomly assigning people to those treatments. When we're talking about homogeneity, it could also be I took a random sample and then I broke people into groups based on some strata, like gender or age or something like that. Your 10% condition, if you are sampling without replacement, you got to make sure those samples are less than 10% of the population. And the large counts condition, remember all expected counts have to be greater than 5. So same as before. And you can see these, here's what it looks like in the College Board from them. This is how you can see those little things right there. That's what they say you're supposed to be checking. So we're talking about phantoms. The P is gone. H and S are a little bit different because the hypotheses and the way we express our answers are going to be different. But the antome part is business as usual. It's the same stuff. Mathematically speaking, they're exactly the same. So when you state the name of your test, it's going to be either homogeneity or independence. You're going to get your test statistic from your calculator along with degrees of freedom, and you're going to get that p-value from there as well. And you could calculate it by hand, but most of the time the calculator can handle it for you. As far as making a decision, you're going to make a decision about Ho, you're going to get that linkage to the p-value, and then you're going to state the conclusion about Ha just as usual. P-value is less than alpha, I reject Ho, there is convincing evidence that there's a relationship between these 2 variables. There is convincing evidence that the distribution is different across these 2 groups. Okay. Remember that when the p-value is low, you're rejecting the null hypothesis because you're convinced about Ha. And if your p-value is greater than alpha, you fail to reject Ho because there's not convincing evidence about Ha. So here's what you need to be able to do. You need to be able to determine the degrees of freedom for a chi-squared test for goodness to fit and for a 2-way test. So you got to know for goodness to fit, it's categories minus 1. And in a 2-way table, since you have categories on both sides, you got to go categories minus 1 times categories minus 1. Or in other words, rows minus 1 times columns minus 1. And we're only looking at observed counts, never looking at totals there. You need to be able to calculate expected values for a goodness to fit test or a 2-way test situation. So in a goodness to fit test, you're just taking like, okay, if it's supposed to be 20% in this category, I take 20% times the sample size. In a 2-way test, you're going to do row total times column total divided by total total. You need to be able to compute the chi-squared test statistic by hand so that you can do that in a formula situation where you're trying to set it up. So you need to be able to find that formula and fill in those numbers using the expected values that you've previously calculated. Remember, the observed values are always the ones that are going to be given to you. And you also need to be able to determine what kind of chi-squared test is needed based on the context of the problem. Now, I promise you that next time we will work on looking at some examples and trying to determine which one is which. But for now, focus on the expected counts and thinking about what these could be. Does it look like multiple groups? Does it look like multiple variables? What's going on? And we will work on that more next time. All right. Thank you so much. Have a great day.